This video is going to cover how to use the lens equations. I will tell you now that it does involve a bit of math, so just be ready for that. You should have your calculator out and be ready to crunch some numbers. So our goal here is to be able to use math to determine the properties of an image. We already know how to determine the properties of an image by drawing ray diagrams and locating where it is. However, that's still just a very crude model for figuring things out. If we use the lens equations, we can actually determine the exact height, location, and distance the image will have as a result of that a particular lens. And so to do that, we have two different equations. First one's called the thin lens equation, which involves the distance of the object, the distance of the image, and the focal point. We also have an equation for magnification. What I want you to do is just verify that your equation is correct. There should be a negative here. So just double check that the formula you have on your page has a negative in front of this fraction here. Also notice that there's two equal signs. Basically what this means is that the magnification is equal to this divided by this, and it's also equal to this divided by this, which means that the ratio of these two numbers should be the same as these two numbers, which is the same as the magnification. So we're going to use those throughout the problems that we're doing today. So on your page you should have a list of these variables. So what I'd like you to do is just to pause the video and fill in these different variables. The first one is distance of the object. So if I have my object here, the distance of the object is the distance from the object to the lens. It is always positive. We never have a negative object distance. Our image, on the other hand, can be either positive or negative depending on where it's located. So if we have a real image which shows up over here, our distance will be positive, and if we have a virtual image that shows up over here, our image distance is negative. So that's the whole point of this table, is to help us figure out if the variable we're using is positive or negative. The other one we have here is height of the object, so how tall our actual object is, and if it's measured upwards, it's going to be a positive height. If our object was down here, we would measure a negative object height. Similar thing goes for the image. If we have an image that measures up this way, it would be positive, so that's an upwards image. If our image is upside down, we measure it downwards and we call our height negative. For a converging lens, the focal length is always positive, and for a diverging lens, the focal length is always negative. Magnification. Magnification will be positive if our image is upright, and negative if our image is inverted. This is a lot of information, and so I don't expect that right away it makes sense. We'll have to do some problems first just to see how things go. So always remember these different variables. Have this chart out in front of you while you're working. You may also want to have an idea of what this diagram shows us. So this is just showing us all the different variables in relation to the ray diagrams that we were drawing before. Let's take a look at this problem here. So I have my lens equations up at the top. There's the thin lens equation and the equation for magnification. Sometimes I need to use one of these, other times I will use both. So in this example we have a converging lens that has a focal length of 17 centimeters. The candle is located 48 centimeters from the lens, and we want to know what type of image will be formed and where will it be located. So our question gives us a lot of information. What we want to do is figure out what that information represents in relation to our lens equations. So we know that we have a converging lens. If we have a converging lens, we know that the focal length should be positive. So therefore our focal length is 17, and it's positive because it's converging. Our candle is 48 centimeters in front of the lens. That means that the distance of our object is 48 centimeters. What type of image and where will it be located? So I can tell that by looking at the distance of the image. So if I know the distance of the image, I know where it is located, and if the distance is positive, I know I have a real image, and if it's negative, I know that I have a virtual image. This is what I want to find. So I have F and DO, I want to find DI. So in this case, I only need the first thin lens equation. I do not need the magnification equation. So I'll set up my equation by first writing it out. I'll plug in what I have. I know that the DO is 48 centimeters, DI is unknown, and my focal length is 17. Using my math skills, I know that if I take this number and I move it to the other side, 1 over x is equal to 1 over 17 minus 1 over 48. Now at this stage, we have a few options. If I really want to be correct and subtract these fractions, I could spend some time finding a common denominator and working through that, but the easier way here is just to make them into decimal numbers. We don't usually do that, but it saves us some time here. So when I do this, 1 divided by 17 is 0.0588. And I'm going to keep 4 decimal places while I'm working through this answer. 1 divided by 48 is 0.0208. So I can subtract these, and I get 0.038. So again, I kept 4 decimal places while I'm working with these fractions. So now 1 divided by x is equal to 0.038. So I have to rearrange and isolate this here. So in order to do that, I will multiply both sides of my equation by x. So those x's eliminate. And I'll be left with 1 equals 0.038 times x. So to solve for x, I will divide both sides by 0.038. And in this case, x is equal to 26.32. And I will keep only 2 decimal places in my final answer. So in this case, x, which remember, this is the distance of the object, or sorry, let's just correct that there. That would be the distance of the image. So the distance of the image is 26.32 centimeters. That's a positive number, so I can conclude that therefore the image will be a real image that is 26.32 centimeters from, so in this case we have a diverging lens, so our focal length must be negative. The distance of the image is 13 centimeters, and again it's a virtual image, so in this case it must be negative. And the distance of the object is what we're trying to find, because that will tell us where the actual marble is located. So if I set this up, what I end up with is 1 over x is, or 1 over x plus 1 over negative 13 is equal to 1 over negative 29. Now, we don't usually write plus minus, right? So really what we're writing is 1 over x minus 1 over 13 equals 1 over negative 29. Using my math skills again, I'll rearrange this. I'll bring this whole thing here to the other side, and I will get 1 over negative 29 plus 1 over 13. Since it's a mess to try and find common denominators between these, what I will do again is use my decimal numbers. So 1 divided by negative 29 will give me this, plus 1 divided by 13, if I have negative 0.0357 plus this other number, I will get 0.0412. In this case, I could go through all of the rearranging that I did in this other problem, or I could jump ahead a little bit and just solve this by doing 1 divided by whatever that number I have is. So that, in this case, x is equal to 1 over 0.0412. X is equal to 24.27. So if I were to interpret this, again, x in this case represents the distance of my object, and my distance is positive, so I could just say that therefore the marble is located 24.27 centimeters from the lens. And that's example 2 complete. Moving on to example 3. A toy car has a height of 8.4 is placed in front of a converging lens. An inverted real image of height 23 centimeters is noticed on the other side of the lens. Determine the magnification. So in this case, we actually have to draw on our magnification calculation. So if you remember, your magnification equation looks like this. And if we read our question again, the height of the object is 8.4, and the image is 23. Now, in this case, it is a real image, and it's inverted. So if we have a real inverted image, our image height must be negative because our image is upside down. So in this case, I have to pick either HI over HO or DI over DO, but I only have HO and HI, so I will pick this right here. So I'm only going to use this part of the equation. Remember, these are two equal signs. So that means that I can use this and this, or I could use this and this, or I could use this and this. So either two I could use to help solve my equation. So I can use this, which means my magnification is equal to negative 23 divided by 8.4, and my magnification is negative 2.73. That seems a bit weird, right? Well, why is my magnification negative? That's because we have a inverted image. So therefore, the magnification is negative 2.73. And there's no units with that. So in this last example, the Lego block is placed 7.2 centimeters in front of the lens, and we get an upright virtual image with a magnification of 3.2. So our magnification is 3.2. It's positive magnification since our image is upright. And the distance of the object is 7.2. What we want to know is where is the image located. So what is the distance of the image? And in this case, I'm talking about distance of the image and distance of the object, so I will pick this portion of the equation and this portion, keeping in mind that there's a negative there. So m equals negative dO over there's an error there. That should be di over dO. So that's going to be negative x over 7.2. And I actually know the magnification. I know the magnification is 3.2. So when I go to solve this, all I need to do is multiply both sides by 7.2. And what I end up with is negative x is equal to 23.04. Divide both sides by negative 1, and x equals to negative 23.04. This here represents the distance of an image. And since my image distance is negative, that tells me that this is a virtual image. So I could say, therefore, the image is 23.04 centimeters and is located, since this distance tells me I have a virtual image, the image is located on the same side of the lens as the object. And that's it. For this last example, we'll do the first problem from the practice sheet. So we want to determine the distance of an image for a 5.5 centimeter tall object that's placed 54 centimeters from a converging lens having a focal length of 20 centimeters. So this is a lot more information than we had in the last example. So if we just focus on what we actually need to find, we actually need to determine the image distance and the image height. So we need two things to come out of this problem. We need the distance of the image, and we want to know the height of the image. What we know is that we have the height of the object, which is 5.5 centimeters. We have the distance of the object, which is 54. And we have the focal length, which is 20. We know that it is a converging lens, so our focal length can be positive. So in this case, we want to figure out, okay, well, what's the best way to go about solving this problem? So I have, I'm given DO, I want to find DI, and I have the focal length. So I can use this equation here to determine the distance of the image. So let's do that first. So we're going to find the distance of the image. So to do that, we will set up our formula. If I rearrange this, I end up with 1 over 20 minus 1 over 54. And what I'll do is I'll just convert each of those to decimal numbers that I can round to 4 decimal places. In this case, I don't need to actually round at all. 0.05 minus 0.0185. One over DI is equal to 0.0315. So from here, I need to solve for DI, so 1 over 0.0315 is equal to DI. And the distance of the image, if I divide those, is 31.76 centimeters. So that's perfect. I have the distance of the image, but now I need the height of the image. So the only formula that has height of image is right here. Now the issue with this is I don't have M, but remember that's fine because I can use either this piece and this piece, or I can use this one and this one over here. So I'll just use HI over HO to solve for the height of my image. So I know that the height of the object is 5.5. DI is 31.76, but I remember I have to put that negative in front. And the distance of the object, or DO, is 54. So from here, what I can do is cross multiply. So what I end up with is 54 times HI is equal to negative 174.68. Divide both sides by 54 to get HI by itself. And I get up with an answer of negative 3.24. And that is remember there's a negative in front of that. That's important. So now I have both height of the image and distance of the object. So I can write my therefore statement. Therefore, the image is 3.24 centimeters tall. It is upside down. I know that because it's a negative image height. And located 31.76 centimeters from the lens. So that's all the information I can tell from the distance of the image and my height of the image. So those negatives and those positives are really useful for interpreting the answer. So we'll leave it there for now. Just go ahead and finish your practice problems.